All right, 3.2, last section. If you are watching this video, congratulations. You have made it to the end of new material in statistics. Okay, 3.2, post hoc tests on one-way ANOVA. Post hoc just means like afterwards, kind of in Latin. So these are tests that you would run on a after you've rejected the null hypothesis in an ANOVA test. And the idea is that you're trying to, if you reject the null hypothesis in an ANOVA, then that means that at least one of the means is different from the others. And so you'd like to narrow it down to figure out which mean or which, what set of means is different from the others, right? And these post hoc tests allow you to make that determination. So to know which means are different, we make pairwise comparisons. So we make pairwise comparisons, and there are lots of different ways that you can do this, but the one that we're going to use is called Tukey's wholly significant difference test, Batman. No, it's just we'll call it Tukey's test for short. But Tukey's test allows us to test mu I equals mu j against mu I not equal to mu j for all means where I does not equal j, which is a fancy way of saying it allows us to compare each pair of means to one another, and it'll do this all at once. In 13.1, we briefly talked about how the probability of making a type 1 error increases each time we do a pairwise comparison. Tukey's test adjusts for this by increasing, Tukey's test adjusts for this increase by changing the test statistic that we use. Here's the test statistic that we used in 11.3. This is for Welch's t-test when we're comparing two means to each other. Here's the test statistic that we're going to use for Tukey's test. Okay, so it's a little bit different, and I'm not going to go through all the mathematics of it, but this test statistic follows the studentized range distribution, which is yet another distribution that we haven't talked about before. But the moral of the story is this: the test statistic and the distribution that it follows are different than they are for Welch's t-test, and these differences make Tukey's test less powerful than Welch's t-test. But they also make Tukey's test more resistant to type 1 errors. So there's a give and take, right? So because we're using a less powerful test, we're also less likely to be rejecting the null hypothesis, which means we're less likely to be committing a type 1 error. And that's a good thing because the probability of making a type 1 error increases for each pairwise comparison we do. So Tukey's test adjusts for that. Tukey's test adjusts for that. Boy, I'm having a hard time talking during this section. Anyway, so the other nice thing about Tukey's test is that it'll do all of the comparisons at the same time. We just have to know how to read the output table, okay? And to run the test in StatCrunch, you would run the ANOVA test, stat ANOVA one way, but then just make sure to check the box that says Tukey HSD, and then it'll make all the pairwise comparisons for you as well. So let me walk you through an example. Okay, this one says, the data in the table represent the number of corn plants in randomly sampled rows for various types of plot. We have a sludge plot, a spring disc, and then a no-till. Part A says, test whether the mean number of plants for each plot type are different at the 0.05 level of significance. So to do that, I'm going to label these things groups 1, 2, and 3. The null hypothesis is that the mean is the same for all 3 groups. The alternative hypothesis is that at least one mean is different from the others. Now, this is just an ANOVA test like we did in 13.1, so there's nothing really new here. We go stat, ANOVA, one way, and let's see what we get. saved all the data from 13.1 because I think we might reuse some of it. But we've got a sludge plot, a spring disk, and then a no-till. Okay, 25, 27, 33, 30, 28, 27, 32, 30, 33, 35, 34, 34, 30, 26, 29, 32, 25, 29. Okay, good. Now we're going to run the ANOVA stat, ANOVA one way. We want to compare these different types of soil. And then here's the Tukey HSD button down here. This is what we'll check on. This is what we'll check on later when we want to do the pairwise comparisons. So I'm going to hit compute, but for now I'm just going to hit compute, right? We get a p-value of 0.0068. Okay, so that's worth writing down. So we say p-value is 0.0068. That's pretty small, small enough definitely to make us suspect that the null hypothesis is not true. So our decision is, since 0.0068 is less than 0.05, we reject the null. So at the 0.05 level of significance, the evidence suggests that the mean corn yield is different for at least one plot type. Okay, and that's that. So now part B says if H naught was rejected in part A. So if the null hypothesis is rejected in part A, then use Tukey's test to determine which pairwise means differ using a family-wise error rate of 0.05. So when they say family-wise error rate, they're just talking about the level of significance for each pairwise comparison that you're doing. Okay. So we want to compare all of the different means. So one of the tests that we're going to run is mu1 against mu2. Okay. Another comparison we want to make is we want to compare mu1 to mu3. And then the last test we want to do is we want to compare mu2 to mu3. Okay, so those are the three tests that we want to run to make our pairwise comparisons. So to run these three tests, we do the same thing that we did before, stat ANOVA one way, but then we're just going to click on compute Tukey HSD. So let's go back to StatCrunch real quick and take a look at that. First of all, notice that here's our analysis of variance table. And if you're looking at the sample means, I would guess that we decided to reject the null hypothesis. That means at least one of these means is different from the others. And to me, it looks like spring disk is quite different from sludge plot and no-till. And I think that that one has a higher corn yield than the others. The others seem pretty similar to me. But let's see if Tukey's test agrees with my analysis. So I just went back and edited this. I'm gonna click on compute Tukey HSD now. And now it gives me a whole bunch of stuff. So in addition to the ANOVA table that it originally spit out, and in addition to the summary statistics that it usually gives us, it also gives us these additional results. And the way that you read this table is that notice that this first table is labeled SP subtracted from. That means sludge plot is being subtracted from, or in other words, compared to, sludge plot is being compared to spring disk. When you compare sludge plot to spring disk, you get a p-value of 0.0122. When you compare the sludge plot to the no-till, you get a p-value of 0.9923. Okay. So remember, sludge plot, we called that group 1. So when we compare mu1 to mu2, we get 0.0122. When we compare mu1 to mu3, we get 0.9923. When we compare mu2 to mu3, that's in this other chart down here, right? Mu2 to mu3, we get a p-value of 0.0154. So let's write down those p-values. Actually, I'm going to write them down so I don't have to remember them, and then I'll switch the view over. But when I compare mu1 and mu2, the p-value 0.0122. When I compare mu1 to mu3, the p-value is 0.9923. And when I compare mu2 to mu3, the p-value is 0.0154. I'm going to switch the view over now. So I've written down the p-values. So making these pairwise comparisons, here we would be rejecting the null. Here we would not reject the null. And here we would reject the null. So reject the null. And I'm going to go ahead and circle the alternative then, because what that tells me is that there's evidence to support the alternative. Here I'm going to not reject the null. So I'm not rejecting it, so I'm going to sort of keep it. This is all loosely speaking, right? We've talked about how not rejecting the null isn't the same thing as accepting the null, but just to make the analysis a little easier, I like to circle these things. Here we're going to be rejecting again. It's in favor of the alternative. So what we see is that mu1 and mu2 are not the same. Mu2 and mu3 are not the same. But mu1 and mu3 are the same. In other words, the mean that's different from the others is mu2, right? Mu1 and mu3 are the same, but mu2 is different from mu1 and it's also different from mu3. And that totally corresponds with what we saw in the sample means, right? Mu1 and mu3 are the same, but mu2 is quite different from the others, okay? And that's what Tukey is telling us, right? So I'm not going to make you write out a full conclusion explaining all that, but I would like you to write out some kind of summary of your results. There are a couple ways you could do it. One way to do it would be to write out the means and underline the ones that are the same. In this case, mu1 and mu3. And then mu2 is kind of off by itself, right? So mu2 is different from mu1 and mu3, but mu1 and mu3 are the same. So that would be one way to summarize the results. The other way to do it would be to write something out and say, it appears that mu1 and mu3 are the same, but that mu2 is different from mu1 and mu3. So something like, it appears that mu1 equals mu3, but that mu2 is different from the others. Okay, mu2. Now that was the spring disk, right? So the spring disk is different. In fact, to be even more specific, you could say it's larger. You could say it's larger. It's larger than the others, right? mu2 is larger than the others, to be more specific. And that's good information. That helps you to answer part C, because part C says, if your goal is to maximize the number of corn plants, which type of plot would you recommend? And well, obviously, there's a statistically significant difference between mu2 and the other plots. And mu2 is larger than the other plots. So mu2 is the clear winner, right? mu2, that was the spring disk, right? So we would say, we would recommend the spring disk plot. Okay, and that's that one. Let's look at another one. This one is that ceramic repair example that we saw in 13.1, right? So you have you're measuring the bond strength of different kinds of repair kits. And in 13.1, we ran the ANOVA on this example, and we discovered they were not, right? We rejected the null hypothesis. So now let's use Tukey's test to find out which pairwise means differ using a family-wise error rate of 0.05. So this time we have a lot of comparisons to make. We need to compare. So I'm only going to write down the null hypothesis here, okay? Just for the sake of time, right? I'm going to say we want to compare mu1 and mu2, mu1 and mu3, mu1 and mu4. And then we also want to compare mu2 and mu3, mu2 and mu4, and then finally we want to compare mu3 and mu4. Okay, so let's go ahead and run these tests. The alternatives are all going to be two-tailed. They're always two-tailed. So that's why I'm not even bothering to write them down. But here I still have that data stored in StatCrunch. So I'm going to go ahead and run the test. I'm going to go to Stat, ANOVA, one way. And I'm comparing these ceramic repair kits. And I want to compute Tukey HSD. Okay, so there's that same p-value that I got when we did 13.1 together, but now we have all these other p-values as well. And so again, to read these tables, okay, Cojet was group 1, Sillistor was group 2, Samara was group 3, and ceramic repair was group 4. So when I compare mu1 and mu2, I get a p-value of 0.8863. I'm going to write that down as I go, 0.8863. When I compare mu1 to mu3, I get a p-value of 0.0382. When I compare mu1 to mu4, I get a p-value of 0.0441. When I compare Sillistor to Samara, so that's mu2 to mu3, I get 0.009. Mu2 to mu4, I get 0.0105. And then finally, when I compare Samara to ceramic repair, that's mu3 to mu4, you get a p-value of 0.9998. Okay. So going back to the notes now, these are the p-values. I can decide whether or not to reject the null hypothesis. Here, I'm not going to reject the null, so I'm going to sort of circle that one. Here, I am going to reject the null, so I'm going to cross it out. So I'm going to say do not reject, and here I'm going to say reject. Here we would reject again. So I'm getting rid of that assumption. Here I'm going to reject. So getting rid of that assumption. Here I'm going to reject. I'm getting rid of that assumption. And here I do not reject. So I'm sort of keeping that assumption. So what we see is that mu1 is the same as mu2, and mu3 is the same as mu4, but there's a wide gulf between those two groups, where mu1 isn't the same as mu3, mu1 isn't the same as mu4, mu2 isn't the same as mu3, mu2 isn't the same as mu4. And that corresponds nicely with our intuition when we just look at the sample means, right? When you look at the sample means, again, mu1 and mu3, mu1 and mu2 look pretty similar. Mu3 and mu4 look pretty similar, but there's a big difference between the groups, right? When we're writing down our summary, we could say something like this. mu1, mu2, mu3, mu4, these two are the same. These two are the same. Okay, and that's that. So on this one, if I ask the same kind of question as I asked on the previous example, like which repair kit would be best? Well, you'd look at the sample means and you'd see that these two have very similar sample means and they're probably the same. These two have very similar sample means and they're probably the same, but these sample means are much smaller than these ones. So you would recommend Cojet or Silastore, right? One of those is probably better than Samara or Ceramic Repair. Okay, and that's that. So let me just say one last thing about Tukey's test. Sometimes Tukey's test doesn't give very good results. There could be a couple ways that it goes wrong. So Tukey's test might say that each pairwise compared set of means is equal, even though ANOVA says that at least one of them is different. In other words, you run the ANOVA, you reject the null hypothesis, so that tells you at least one mean is different from the others. But then you run Tukey's test to find out which mean is different from the others, and you don't reject the null hypothesis on any of the pairwise comparisons. That would be a contradiction, right? In that case, Tukey's test is contradicting ANOVA. The reason this happens is because ANOVA is more powerful than Tukey's test. Okay? In that case, chances are ANOVA is making the correct decision, but Tukey being less powerful doesn't help us figure out which means are different from the others. Okay? So that's one way that Tukey's test could go wrong. It could go wrong because it contradicts ANOVA. Another way that Tukey's test could go wrong is that it could contradict itself. So after making all of your pairwise comparisons, you might end up with a scenario like this, which is impossible, right? This thing is saying that mu1, mu2, and mu3 are all the same. It's also saying that mu3 and mu4 are the same. But then it's saying that mu2 and mu4 are different, and that mu1 and mu4 are different. But how could that be? If mu1 and mu3 is the same, and mu3 and mu4 are the same, then mu1 and mu4 would have to be the same, right? But this is saying that mu1 and mu4 are not the same, and that's clearly a contradiction. Basically, this means that at least one type 2 error has been committed, right? Because somewhere we failed to reject a false null hypothesis. So whenever Tukey gives contradictory results, either with itself or with ANOVA, we just say that the test result, that Tukey's test is inconclusive, and that's just our answer to that. So let me give you an example where this happens. This one says the data in the table represent the number of pods on a random sample of soybean plants for various plot types. Different plot types this time though, and different crop. We're not looking at corn, we're looking at soybeans. But anyway, Liberty, no-till, and chisel plowed. A researcher wanted to determine if the mean soybean yield differed for different plot types. One way ANOVA resulted in rejection of the null hypothesis with a p-value of 0.038. Which pairwise means differ? Well, let's see. So first we have to enter the data into StatCrunch. So let's do that. Okay, so we're going to go to stat, ANOVA, one way. We want to compare these plot types, and we want to run Tukey's test. Sure enough, we get that p-value that they said we would get for the ANOVA. And then as far as the pairwise comparisons are concerned, it looks like when we compare mu1 and mu2, we don't reject that, so mu1 and mu2 are the same. When we compare mu1 and mu3, we do reject that, so mu1 and mu3 are different. But then when we compare mu2 and mu3, we're not rejecting the null hypothesis there, so mu2 and mu3 are the same. That's weird, right? Let's write this down. Okay, so that we understand what's happening. Whoop. Okay, so in other words, if I compare mu1 and mu2, mu1 and mu3, and mu2 and mu3, well, for this first comparison, I get a p-value of 0.8575. For this second one, I get a p-value of 0.0404, and for the third one, I get a p-value of 0.1182. Okay? So here, I do not reject, right? Do not reject. Here, I do reject, right? And here, I do not reject. So now if you think about what this means, what we're saying is that mu1 and mu2 are the same, mu2 and mu3 are the same, but mu1 and mu3 are different. That can't possibly be, right? If mu1 and mu2, if mu1 equals mu2 and mu2 equals mu3, then by the transitive property of equality, mu1 equals mu3. Right? It must be the case. And yet we're getting this contradictory result. So if you were to try to write that out, it would look something like this: mu1, mu2, mu3. These two are the same, and these two are the same, but these two don't match, which is a contradiction, right? So Tukey's test is giving us contradictory results here. We would say something like Tukey's test is inconclusive. Okay, and that's your final answer. Okay. And that, my friends, is it. That is it for an introductory statistics course. It goes without saying that there are lots of other kinds of hypothesis tests you could do. There are lots of other kinds of sample statistics you could compute. There are lots of other kinds of graphs that you could put together. But these are the sort of mainstays of statistics. And if you want to know more statistics that's more specific to your area of study, then you will learn those, right? If you're going to be doing research anywhere, then probably you're going to do some more statistics, but that's more specifically geared toward your area of study. But it's all going to build on the stuff that we talked about in this class. If you're never going to do research, then even still, right, it's nice now to know what the p-value is if you're reading some kind of research paper or whatever. It's nice to know what the mean is and what the standard deviation is, right? All of these things are important and they come up in life. So that's that for statistics. Maybe one more thing I should say before I go is that in this section, we ran Tukey's test on all three examples that we looked at. But remember that you only run Tukey's test if the null hypothesis is rejected when you run the ANOVA. If you do not reject the null hypothesis in an ANOVA, then it's not appropriate to run Tukey's test, because if you don't reject the null hypothesis in an ANOVA, then ANOVA is telling you that the means are all the same. So there's no need to run Tukey's test to try to figure out which means are different from the others, right? Because ANOVA is already telling you that all the means are the same. And I think that's all I have to say about that. It's been a pleasure.